Welcome to A-Level and AP Physics. In today's lesson, we will discuss a typical type of question on electric field from May June 2021, paper 4.1. In this lesson, we will discuss how to sketch electric field against distance for an isolated matter sphere. I will also explain you how to sketch de Broglie wavelength of a particle against its momentum. At the end of the video, we will also discuss how to sketch the number of daughter nuclei against time. For part A, it is given to us an isolated metal sphere of radius r and electric field at its surface is given, that is E naught. This sphere is charged and electric field at its surface is E naught. For this question on figure 6.1, we need to sketch the variation of electric field E against distance x from the center of the sphere. We need to sketch from x is equal to 0 to x is equal to 3r. First of all, let's try to understand how the electric field of metal sphere look like. If you look at this metal sphere, you can see there is electric field that is outside of the metal sphere, but there is no electric field line inside this metal sphere. This is simply telling us that there is no electric field inside metal sphere. Later we will discuss why there is no electric field inside metal sphere. First of all, let's try to look at the electric field outside of the metal sphere. Electric field outside of the metal sphere we can relate with distance from the center of the metal sphere by this simple relationship. E is simply equal to kq over x squared, and x is the distance from the center of the metal sphere. Now if you look at this equation, we can simply rearrange this one. We can write down Ex squared, this is equal to kq. Q is the amount of charge on the metal sphere that is constant, and k is also constant. It simply means that the product of E and x squared, this is constant. So simply we can write down this is constant. We can also say that it simply means that electric field E1 at distance x1 squared, this will be equal to E2 times x2 square, and this is also equal to E3 times x3 square. Now what exactly it means? Let's say when the distance from the center of the sphere that is equal to r means just at the surface, so we can say simply at this point, then electric field is equal to E naught and this distance is r. So this is r square. Let's look at a point that is at a distance of 2r. As you can see here, x is equal to 2r, so electric field at this point is E2. Now as the distance is double, so this is our electric field E2, distance is double, so means this is 2r square. This has to be E naught divided by 4 because the product has to be the same. If we take another point, let's say we take this third point that is at a distance of 3r from the center of the sphere, from the center of metal sphere, then the value of E3 that will be equal to E naught by 9 because the distance is triple. In this case, now we have found the value of electric field at the surface, that is E naught. This is already given to us that the electric field at its surface means at a distance of r that is equal to E naught. That's the reason we have written this is E naught. If the distance is double from the center of the sphere, electric field is 1/4, and if distance is triple is 3 times, electric field is equal to E naught by 9. So these are the points we need to understand to draw electric field outside of metal sphere. Let me show you how to sketch. You can see here at distance r, electric field, this is E naught, so electric field here, this is E naught. At a distance of 2r, electric field is E naught by 4, so electric field here is E naught by 4, means 1/4 of electric field at the surface. And at a distance of 3r, electric field is E naught by 9, and then we need to sketch this curve. This is what you need to do for this question for the electric field outside of metal sphere. Let me explain to you why the electric field inside the metal sphere, this is equal to 0, means electric field here means from the center to the surface electric field inside this metal sphere, this is equal to 0, as I have already explained here. Let me explain to you this one with very simple example. Let's say we have this metal sphere and we add some charge on this metal sphere. Let's say this is the charge we have added on this metal sphere. What will happen is that this charge will not stay here. You need to understand the reason is that because this is metal, this is a conductor. So these charges, there is repulsive force between these charges will repel each other, and finally these charges, they will stay at the surface of the metal sphere, and these charges, they will be evenly distributed, and when they are evenly distributed, finally the electric field inside this metal sphere, that will be equal to 0, because these charges inside the metal sphere, they will cancel electric field, so there will be no net electric field inside the metal sphere. But these lines outside of the metal sphere, they appears to come from the center of the sphere, but inside the sphere electric field is cancelled. These charges, they cancel electric field of each other, and when they're evenly distributed, there will be no net electric field inside metal sphere. So this is what you need to understand. We can also understand this concept in a little bit different way. We can also use Gauss's laws, we can also use, but this is not part of A level, but if you're curious about this one, we can also use Gauss's law. According to Gauss's law, the closed integral of E dot dA, so E is electric field and A is the area normal vector, this is equal to Q enclosed divided by E epsilon naught. Q enclosed, this is the charge inside Gaussian surface. If we draw our Gaussian surface here, inside the metal sphere, there is no net charge enclosed inside this Gaussian surface. So it means Q is equal to 0. So if Q is equal to 0, it means electric field is equal to 0. So this is mathematical proof of this, why electric field inside metal sphere is 0. Let's try to understand what will happen when we place a neutral metal sphere inside an external electric field. As you can see here, when we place this metal sphere inside electric field, electrons will be attracted in direction opposite to the electric field. So you can see here, this side become more negative and this side become more positive because this has less number of electrons. So in this case, you can see the positive charge is on one side, negative charge is on the other side. So there is an induced electric field that is inside this metal sphere, and this induced electric field, this is opposite to the external electric field, and this induced electric field will go on increasing until the magnitude of induced electric field is equal to external electric field. Means the magnitude of these two electric fields finally will be equal. So when it is equal, so these two electric fields, they will cancel each other, and the net electric field, let me draw the lines inside. You can see this is external electric field and the red one, that is induced electric field. So when the magnitude of these two is equal, then the net electric field inside metal sphere, again this will be equal to 0. So this is example of shielding, so electrostatics shielding. So this is E, this is equal to 0. So in this case, electric field inside metal sphere is also 0 when we place this one inside an external electric field. Same concept we can also use to explain this one, mean an isolated metal sphere, why electric field inside isolated metal sphere is equal to 0. Let me explain to you how marks are distributed for this question. If you have shown from x is equal to 0 to x is equal to r, electric field is equal to 0, mean if you have drawn this horizontal line, you will get 1 mark, and this is B1 mark. The second mark you will get if you have drawn curve that has negative gradient of decreasing magnitude, means you have drawn the curve like this, you will get the second B mark. And the third mark you will get if you have shown at distance of 2r, electric field is E naught by 4, and you have also shown that at a distance of 3r, electric field is equal to E naught by 9. Then you will get the third B mark. So this is how marks are distributed for this question. For part B, it is given to us the de Broglie wavelength of a particle is lambda naught when its momentum is p naught. On figure 6.2 means on this figure we need to sketch the variation with momentum of the de Broglie wavelength of the particle for values of momentum from p naught by 2 to p naught. So this is p naught by 2 to p naught. In order to sketch graph between these two quantities, we need to understand the relationship between wavelength and momentum, and that is simply equal to lambda is equal to h over p, and p is the momentum of the particle and lambda is the wavelength of the particle. It is given to us the de Broglie wavelength of the particle is lambda naught. Simply let's say this is lambda naught, and the momentum is p naught. At this wavelength, this is the momentum. If we rearrange this one, we can write down lambda naught p naught, this is equal to h. H is the Planck's constant, so this is constant. Simply we can write this is constant. Next thing we also need to understand, when the momentum is half, means this momentum of the particle, this become half. Lambda, this has to be double, 2 times of lambda naught, because the product of these two quantities, it has to be equal to h. This is what we simply need to understand. So these two quantities we can also understand. We can write down here lambda, this is inversely proportional to momentum of the particle. We can also write down like this. Now we need to sketch the graph between these two quantities. Graph will be rectangular hyperbola. So let me show you how you can sketch the graph. This is how you can sketch the graph. This is simply how you need to sketch. And for this question, there are 2 marks. Let me explain to you how these marks will be awarded. The first mark is if you have drawn a curve with negative gradient of the decreasing magnitude and it is passing through p naught and lambda naught, and its gradient is negative and gradient is decreasing. And the second, so this is 1 mark, so this is B mark, you will get 1 mark. And the second mark you will get if your line is passing through p naught by 2 and 2 lambda. So this is p naught by 2 and 2 lambda. So this is p naught by 2 and this is 2 lambda. So this is the second mark. This is second mark. So the first mark p naught lambda naught. So this was the first mark. You got 1 B mark. If you have drawn the line, means you have drawn this curve and its gradient is negative and gradient is decreasing and it is passing through this point. You got 1 B mark. And if it is passing through 2 lambda naught and p naught by 2, you got the second B mark. So this is the second B mark. For part C, it is given to us a radioactive isotope decays with a half-life of 15 seconds to form a stable product. The radioactive isotope at time t is equal to 0 contains n naught number of nuclei and there is no nuclei of the stable product. Question is asking us to sketch on figure 6.3 the variation with time of the number of nuclei of the stable product for time t is equal to 0 to t is equal to 45 seconds. T is equal to 0 here and t is equal to 45 seconds here. We need to sketch on this figure 6.3. In order to answer this question, first of all, let's draw one simple table and then we will sketch this graph. Let's say we have 3 different columns. In the first column we have time and in the second column we have number of parent nuclei. This is number of parent nuclei, and in the third column, let's say we have number of daughter nuclei, or simply we can say product nuclei. I will simply write down number of product nuclei. So this is number of product nuclei. At time t is equal to 0, there are only parent nuclei, so that is equal to n naught, and there are no any product nuclei. So this is 0. After time equal to 1 half-life means T1 by 2. This become half means this become N0 by 2, and the daughter nuclei are the product nuclei. They also equal to N0 by 2. We can also say this is equal to 0.5 of N0. After 2 half-lives means 2 times of 1 half-life, this will decrease to N0 by 4, and the product nuclei, they will increase to 3N0 by 4. Or we can say that that will be equal to 0.75 of N0. After time equal to 3 half-lives, so 3 half-lives, this will decrease to N0 by 8, means the parent nuclei, and the number of daughter nuclei, they will increase to 7 N0 by 8. So this is just basic calculations based on half-life, and that will be equal to about 0.88 N0. So this is about, actually the exact number is 0.875. Approximately we can write down 0.88 N0. That's all what we need to understand, and now we need to sketch. It tells us after 1 half-life means after 15 seconds this become half, so this will be here, so this become half. And after 2 half-lives, this is 0.75, means this is after 2 half-lives, so this will be here. And after 3 half-lives, this will be 0.88, so that will be around here, 0.88. And then we just simply need to sketch. Let me show you how you can sketch the graph. This is how you need to sketch. And this question has 3 marks, so let me explain to you how the marks will be awarded. You can see the first mark will be awarded from time t is equal to 0 to t is equal to 45 seconds, mean from here to here. If you had drawn the curve with positive gradient, as you can see the gradient of this line is positive, but the gradient is decreasing, and it has to start at 0, 0, means if it is starting from here, so you will get 1 mark. So this is B1, 1 mark. If the line is passing through 15 and N0 by 2, means if the line is passing through this point, you will get the second B mark. And the third B mark is if the line is passing through 30, 0.75 N0 and 45, 0.88 N0, when it's passing through this point, you will get the third B mark. This is how marks are distributed for this question.